Hey everybody, welcome back. So last time we looked at the very important intuition for the algorithm of gradient descent, which basically said something like this, where if you have whatever function, for us, we were thinking about our cost function called the MSE, which maybe it looked like this with respect to maybe beta naught, okay? So if we're looking at the MSE with respect to beta naught, that means wherever I put beta naught here, this is what the MSE value is. Now, we want the lowest MSE value, okay? This is our cost function. It's our function that's saying how good or bad our model is. We want to get this to the bottom, okay? So we're trying to train our model, and so we're trying to pick the right beta naught, and as well as other parameters to do that. But what we want to do is instead of just solving all at once, we want to just get this iterative algorithm that says, okay, I'll look at the derivative at this point, and then I will go this way. Okay, I'll look at the derivative at this point. Okay, I'll go a bit this way. And so we actually didn't look at a couple different pieces of it. One is that we didn't talk about how far we're going to be moving each step. We did talk about how we'll be going down and down and down and eventually stop at the bottom here. But we didn't talk about the size of the jump that we're going to be moving. We really just talked about, okay, if the derivative here is, say, positive, okay, if the derivative, that's a bad color to pick, if the derivative at this point is positive, well, that means I want to go to the left because if I went to the right, I'd be increasing. So if I go to the left, I'll be decreasing. Okay? So we keep doing that over and over again until we get to the bottom. Except, how big of a jump are we going to take? And also, how do we know when we're done? Okay? How do we know when we hit the bottom here? Because, could we have gone further? I don't know. All right, so we're going to talk about these steps, and it actually described the gradient descent algorithm for linear regression. Okay, this is probably going to take 2 videos, but today what we're going to do is remind ourselves first that we need the derivatives of the MSE function. And so just to remind us again, that's a bad color because I picked that a few too many times. The green, the MSE, again, you've seen it before, 1 over n times the sum as I goes from 1 to n of, and I'm going to write it, this is yi, okay, but then minus, and actually I think I usually do the other way around, so I'll keep consistent with this. So this is yi hat, which is actually, for simple linear regression, it's going to be beta naught plus beta 1 xi. Okay, that's our best guess, and then we'll take the difference of that between our actual and we'll square the results. Okay, so that's our MSE function. And if we remind ourselves of way before, I don't expect you to remember this because even I didn't remember this. And we'll find out today if I ever did make an error deriving the derivative, because now pretty soon we'll actually find out in code whether this works or not. So partial MSE, and this is just writing down from somewhere else, don't expect to understand this. The derivative turns out to be 1 over n times the sum. So I goes from 1 to n of 2, because that squared came down to be a 2. And then we'll have beta naught plus beta 1 xi, and then again, minus yi. And so with beta naught, that's actually it. That happens to be the derivative. And so the MSE with respect to beta 1 is exactly the same thing, except one minor change. So it's all of this stuff to, this is exactly the same inside here, no changes at all. And then what we do is multiply this by xi, and that kind of makes sense because you can see this beta 1 is attached to that xi, so we'll end up multiplying by that. So here's our derivatives, and so I only have the graph drawn for beta naught here, except this is going to work for beta naught and beta 1 so that we find the best parameters for all of our parameters, not just one of them. So we look at these derivatives and maybe the function something like this, I don't know. And basically we would keep evaluating the derivatives here. And so we would say, okay, if you're here, well, then what's my derivative? I'd ask this value. Okay, that's particular on the data points, which is the x, the data point, which is the y, and most importantly, it's particular based off of our actual values of beta naught and beta 1. And so what these are whatever they are currently. Okay, so beta naught is this, and maybe beta 1 is this. We'd ask what the value of this thing is. Okay, well, if it's positive, and so it should be positive here, our function's increasing here. And so that means we would want to go to the left. So we take some jump down here. So how big a jump do we want to take? Well, we want to take it based off of 2 things. One, based off of how big that derivative value actually is, because if you picture it, you can see here, okay, the function's very, very steep, and so clearly we've got a long way to go until we get to the bottom. So we're okay with a big jump to the left, that's fine. But then maybe we do that jump, and then maybe we're somewhere over here, and we can see, okay, it's actually starting to smooth off a bit. You see, our slope is just a little bit less steep than the other one. Okay, if I was to draw these out a little bit more, this slope is like this, and then this slope is like this. Okay, it's less steep. And so we're okay maybe with a smaller jump. Okay, maybe we'd prefer just a smaller jump that goes maybe only to here. Okay, we did less distance this way. All right, and then again, it's going to happen with, I'll do a final color here in red, is that, okay, it's really smoothing off. We're going to go actually just a smaller jump here, okay? And that's, you can see if I extend the slope, it's a less slope than the other one, okay? The derivative value is smaller, that slope is less, and so we want to take a smaller jump in that direction. So we want our jump to be based off of the value of the derivative. And in particular, the higher the value of the derivative, that means our function is more like jumping like this. And so we've got a bigger jump to do. We need to go more to the left or more to the right. And so basically, the bigger the value of the derivative is, that is going to dictate the jump, okay? So we care about the direction because we want to go left if the function is increasing, okay? We don't want to increase the MSE, we want to decrease it. So we'll go left if it's positive and right if it's negative. Okay, again, remind you, this is negative, and so we want to go to the right. And again, these are positive slopes, and so we want to go to the left because we want to get down here. And at the same time we're making these changes for beta naught, we'd also have some value of beta 1, and we'd be doing something very similar with respect to its derivative. We'd keep asking this thing, and we're saying, okay, are you positive or negative? Well, I want to make sure that I move in the negative direction so that I go towards the bottom. Okay, I want to move in the opposite direction. And so I always want to keep minimizing and taking steps that are smaller and smaller like this because I don't want a jump that's going to be super big. If I did keep doing the same jump that if I had a function, if our function was like this up here, and so we'd be taking a really big jump up here, it says, okay, clearly we've got a long way to go like this. Well, actually, it turns out that if we were down here and doing a jump like that, if we were going to move a lot to the left, well, that would move past it. And so we don't want to do that. That's why we try not to do that. We consider the value of the derivative. And so the next video, I will derive for you with respect to beta naught and beta 1, the actual algorithm to do this.